Okay. Good morning and welcome. As part of the daily activities of the 2021 edition of ITASEC, I'm glad to share this track about field security.
Ma comunque no, ma chi deve essere una doppia virgoletta? Perché non deve essere una doppia virgoletta?
Sorry, someone has the mic open. Please mute yourself. My name is Luigi Coppolino, and I'm an associate professor at the University of Naples Partenomen, and actively working on field security as partner of the Untitled H2020 project, and formerly of the Confido H2020 project. Field security is by itself a critical topic since the sensitivity of the data and of cyber physical nature of the system. But since the start of this awful pandemic, health and remote healthcare have played a major role. As a consequence, we witnessed a sudden increase in the number of attacks in the health sector, which actually doubled in the last year. This said, I'm willing to pay attention to the next presentation on the topic, and I anticipate my greetings to all of the authors that contributed to this session. Usually I leave the floor to the first speaker, that is Domenico Lofù, who will tell us about an artificial intelligence cyber attack detection system to improve threat reaction in here. Please, Domenico, take the room.
Okay, can you hear me?
Yeah, very well.
Perfect. Good morning, everyone. Thank you for presentation. I'm Domenico Lofù, and currently I'm an industrial PhD student at Polytechnic University of Bari. I'm also an employee of Esprivia, an international software company whose main headquarters is located in southern Italy, 13 kilometers from Bari. The work I'm going to present is being carried out with the co-authors, whose name you can see in this slide. In this work, we propose a cyber attack detection system that is able to identify compromised data during a cyber attack and support the caregiver to fix the problem. Okay, we can go to the next slide. First of all, let me introduce the framework in which this research can be contextualized. We are in the context of the security in the health. The system description is contextualized on the case where an IOMT system has been hacked with the malicious intent of manipulating health data in order to trigger bogus care countermeasure. The Internet of Things has transformed the hospital setting and created a new moniker for the healthcare world, the Internet of Medical Things. Ensuring a security mechanism for IOMT in a distributed device is a challenging issue. Can go to the next. Patient monitoring devices are then connected in the IOMT network. In turn, edge devices communicate with the cloud infrastructure to store gathered clinical data and keep in touch with the corresponding medical staff. Therefore, some vulnerabilities may arise regarding the security of patient and clinical data. Compromising security in any health system can lead to serious damage to patient health. In particular, in a remote care context, the protection of telemonitoring system of patients are essential to ensure that they follow their clinical pathway without a kind of external intrusion. We can go to the next slide. The slide highlights the contribution of artificial intelligence to health system. Artificial intelligence play an important role in combating cyber attacks on the security of patient telemonitoring system. A system that monitors and prevents cyber attack in healthcare not only must detect the attack, but should also be able to properly understand and report it to the user. In particular, anomaly detection systems are a renowned approach that are based on machine learning or deep learning methods to model normal activity in a such way as to easily detect abnormal deviation from the standard in a data-driven fashion. Therefore, in a such sensitive domain where several healthcare professionals are involved, it is important to represent and explain threats in explainable manner. Moreover, current detection model and rule are not mature enough to recognize early breaches that have not yet caused any damage. Our paper suggests the use of Cyberattack detection system model that exploits a technique to detect anomalies without requiring a security analyst provide feedback to the personnel, healthcare personnel. In this slide, we can see an overview of the system architecture that is focused on the security of data transmitted from IoMT sensor to three different interconnected process modules. The clinical pathway anomaly detection, the explainer, and the user interaction engine. The technological infrastructure promotes the care of a patient accordingly to HERO clinical pathway that is a care process composed of multiple clinical guidelines. The proposed Cyberattack detection system implements cybersecurity methods to identify which data were compromised after the system is hacked. It also provides an explanation of the cyber attack and enable interaction between the remote detected anomalies and care phases. In particular, the anomaly detection phase is carried out by the CPAD module that detect deviation from the patient clinical path and avoid the processing of inconsistent or false data. After the detection phase, the explainer module analyzes clinical data classified as anomalous and through the user interaction engine send a validation request to remote medical staff. We can go to the next slide. This slide shows the relationship between the various modules in terms of data flow. Anomalous data, which represent an intrusion in a hacked system, are explained accordingly to explainable security paradigm. As a result of a hacked home care telemonitoring system, the Cyberattack detection system classifies some HEG instance as false positive or false negative. After the detection, the user will be able to analyze the characteristics of what caused the declassification of some data as false positive or false negative and interact with it. The interaction activity with the data is performed by means of the user interaction engine, which provides a dashboard to visually explore the data to have a clearer view of what happened. Furthermore, thanks to the user feedback submodule, it's possible to improve the classifier and consequently the anomaly detection and identification of threats. We can go next. Referring to the previous running example, it's reported the formal definition where HEG is a function of Earth-bit. We can go next. Once the data have been transformed into a structured form, they are input to the CPAD, which analyze and check them to detect the anomaly. The CPAD module is based on a robust deep encoder. It is assumed that the cyber attack on HEG measurement is going on. A delayed threat reaction would compromise the patient care pathway. By exploiting RDA for anomaly detection, ensure a rapid response in terms of inference time, quickly detecting anomalies. The CPAD module defines three sets of classified HEG data that are reported in the slide. Once the structured data have been processed, the CPAD produces a CSV file with all the instances classified as anomalous. The autoencoder is based on a training pipeline where examples of anomalies are provided during model training. At the end, the CPAD module separates the predicted instance into the three different sets. We can go next. The next step is to interpret and explain the set created previously to understand why certain instances have been classified as anomalous. In system using explainable AI algorithm, additional data coming from the machine learning process may be useful explanation produced by the system itself to enrich the predicted instance with a plausible rationale. Explanations are therefore designed to bridge the gap between actual safety and perceived safety. The explainer module of our cyber attack detection system receive input from the API gateway and the CPAD. Exploiting ITASEC paradigm, the aim is to obtain its 6 double that give a complete view of the anomaly. It requires a dedicated reasoning tool to infer and reach knowledge about the security aspect. We can go next. In addition to ITASEC paradigm, two specific design and index are introduced. The anomaly score general unsafe reported in this slide, and we can go next. And anomaly score class unsafe. For details, you can check the paper. In this case, previous slide. Okay. In this case, the higher the value of the ASCII score, and therefore to closer to 1, the more abnormal the heartbeat will be in the set of heartbeat of the same class. Okay, you can go next. The explanation module therefore acts in two conjunction phases. The first one takes the output of the CPAD and index. The second is output of ITASEC paradigm. The CPAD system provides the doctor a concise explanation of the anomalies through to visualization framework. We can go next. Okay. In our case study, the contribution of the user feedback to the system is the evaluation of the detected anomaly and the embedding of a doctor feedback. The user feedback module will generate for each detection a feedback coefficient that represents the doctor feedback on a given instance. Following the explanation, it's possible to check whether the clinical pathway that has been generated is correct or not. It uses an algorithm of visual data mining that allow, through different visualization techniques, to interactively group data in a more efficient way, improving the data insight process. You can go next. Afterward, the user interface included in the user interaction engine allow the user to interact with the data. After the explanation module has displayed the result of the ITASEC paradigm, it's possible to visually manage each HG detection. Through the integration of CPAD, explainer, and the user engine interface module, the visualization framework will be able to manage anomalies detected as threat insight. This will be appropriately displayed on the user interface, which, in addition to allowing interaction with the anomalous data, in this case, the HG detection. Thanks to the threat graphically representation in the dashboard, the user reaction to the threat is improved. You can go next, okay. We've looked at the main contribution of this paper about how it's possible to improve user reaction to threat in healthcare telemonitoring system using AI technique. The proposed work witnessed how the wide range of AI technique are already dramatically important in the hot topic of cybersecurity, in particular when applied to the health domain. The effectiveness of artificial intelligence algorithm in identifying threats and the consequent efficiency in significantly reducing the user reaction time are becoming fundamental property to be taken into account when designing a cyber attack detection system. For this reason, threat intelligence is increasingly becoming a tool for enhancing system security and performing automating threat analysis. Future work will be devoted to the integration of other IoT sensors and hence to the anomaly detection of other vital parameters. We can go next, and I would like to thank you for your patience listening to me and the error of the presentation. I will be happy to answer any question you may have. Thank you.
I don't know if there is any question you can write in the question and answer section of the chat. In the meanwhile, I have a question. Domenico, is there any preliminary results in terms of, I don't know, latency or false positive or reaction times and so on that you can tell us about, or you have already some experience with your system and approach?
Okay, now we have implemented the part related to the clinical path anomaly detection. We are developed the algorithm and we have the code that it's ready. And the next step is make the algorithm on the edge infrastructure. Now we don't have any result regarding to implementation on the edge infrastructure, but I hope that we arrive as soon as possible.
Okay, thank you.
Thank you.
Let's go to the next presenter. That is who is Fabrizio Marangio, and Fabrizio will tell us about a blockchain-based smart contract system architecture for dependable health processes.
Good morning to everyone. I am Fabrizio Marangio. I am a research fellow at the ICAR Institute of the National Research Council of Italy and a PhD student at the Partenope University of Naples. The work I'm about to present will concern the use of a blockchain system for the validation of healthcare processes. I will start with a brief introduction about the context of interest and the purpose of our work. We will then move on to analyze the architecture of the system and finally show a case study to define its feasibility. The digitization process has strongly affected the healthcare environment, bringing significant benefits. We can think of how much easier it is for physicians to consult their patients' clinical records, or how data collection for scientific research purposes is greatly simplified. Obviously, in order to encode the data in the right way, there is the need of some reference standards. Actually, various standards have been developed in healthcare, and recently the FHIR standard is rapidly gaining acceptance. This standard requires that data be sorted in the precise structures called the resources. So we have resources defining patients, doctors, medical examination, and so on. These resources are exchanged through REST interfaces, and the range of resources that can be used is constantly being refined. To ensure that health records can be used quickly and efficiently, the use of appropriate standards is not enough. We need to a level of interoperability between the systems used, and considerable efforts have been made in this respect in many countries of European Union. And the map shows the countries participating in the Connecting Europe Facility program, designed to improve interoperability between European countries. In Italy, for example, we have the National Interoperability Infrastructure that has been designed to ensure interoperability between regional systems to a centralized national infrastructure. Although the efforts made are considerable, ensuring the interoperability of systems and create appropriate standards does not exhaust the problems of a very complex context such as health. Data are produced through processes that are defined by the health authorities, but the actual processes by which the data are produced do not always comply with the indication. So we have the standards, we have frameworks to enable interoperability. Moreover, there are many proposals of blockchain systems for the healthcare, but these systems are focused on data integrity and authentication. And however, at best our knowledge, few has been done about validating the healthcare processes by which the data is generated. The aim of this work is to couple a blockchain system with an application layer so that by means of appropriate smart contracts and exploiting the intrinsic immutability properties of the blockchain, it is possible to guarantee the validation of healthcare processes by verifying the adherence of the process, as indicated by health authorities, with those actually in place in the system. In this slide, we can see a description of the architecture. The file resources are stored and managed by the file servers in dedicated databases. Blockchain clients act as a bridge between the two layers by receiving information from the application layer and launching the appropriate transaction on the blockchain layer. The interfacing between the two layers can be created through modules that can hook up at various points in the processes, and the happy file implementation provides modules called interceptors that are created for this purpose. About the service layer, we have a REST interface that is the interface through which the user sends requests and receive responses from the system. Then we have the access control module that implements the authorization phase according to specific access policies. The process request manager that collects and organizes all the information useful to identify the process to be considered as a template and send this information to the information manager module. Then we have the workflow verification modules that request the activation of a specific read transaction at the blockchain layer. And this interaction allows the retrieval of all the activities already carried out for the specific process. This information allows the module to effectively check the adherence between the activities received in input and the process template. The information manager interacts with the process management module to identify the templates of the current process and retrieving them from the process template B, and communicates with the workflow verification module to verify adherence to the process by providing the reference template and the rules to be followed as defined in the rules to be. The storage manager allows the management of the information stored in the database managed by the resource to be module, such as the sequence of the tasks for a specific health process or the required resources. Well, as regards the blockchain layer, we have smart contracts, which will be composed of create, update, and read transactions. So basically, we have a distinction between read and write transactions. The assets will be composed of a hash digest of the file resources and the references they contain to other resources. This means that no unencrypted data about the patient or examination performed will ever be saved on the blockchain. The assets will be saved on the ledger that will be read through the appropriate transaction during the validation phase. We choose a private permissioned blockchain because this type of blockchain is well suited to the healthcare context, which could be organized in consortia and requires authentication and well-defined rules. The chosen operating platform is Hyperledger Fabric, as its modular approach allows a complete and simple integration with the system designed. The endorser, orderers, and committers through which the testing, sorting, and validation operations are carried out can be chosen from among the healthcare organization, so there is no one-to-one mapping with the users of the application layers. By combining the concepts outlined, we can easily understand the general flow of the architecture. As you can see in the image, the information manager will manage a series of tasks. These are the activities that can be carried out within the healthcare process, And we can think of a prescription, purchase of medical devices or drugs, diagnostics exams, and so on. The active task will be converted into an asset on the blockchain and saved in the ledger. Through the verification module, it will be possible to read what has been saved in the ledger and compare the hash digests saved in the blockchain with the template verifying adherence. This means that no control will be carried out on the data, such as the patient's personal data, but by cross-referencing the hash digest of the assets, it will be possible to verify that all the process steps have been carried out in the correct order. In this scenario, we see how our architecture can be applied to a real case. A patient, following a medical examination, receives a prescription for cholecalciferol and goes to a pharmacy to pick up the medicine. Then, after dispensing, an activity regarding this dispensing of the medicine is recorded in the application layer, and consequently, a transaction will be launched in the blockchain to create an asset related to this activity. The asset created will contain not only the hash of the activity itself, but also references to the previous ones, so prescription and visit. At this point, the adherence of the process can be checked. At the application level, it will be verified that the rules for the prescription have been followed. So in this case, that there is a diagnosis of hypocalcemia. And through the blockchain, it will be possible to reconstruct the chain of activities in the order in which they were carried out. By combining the information, it will be possible to verify the complete adherence of the process to the guidelines. During this process, we will have a total of 4 read transactions and 3 write transactions on the blockchain. The question that arises is whether, given the amount of healthcare processes that are performed every day and no scalability issues of blockchain system, it would be feasible to use such a system. In this slide, we show data from Italian drug agency, and we can see that we have about 1.6 million of prescription processes in a year, that considering the day hours, that are about 500 processes in an hour. But what about the blockchain performance? We know that recent studies on the performance of Hyperledger Fabric show that it's possible to have a number of transactions per second in the thousands. From the image, we can see that there is a considerable variation depending on whether there are more or fewer write transactions than read transactions, and how performance change depending on the filters applied. However, these studies help us to get an estimation of the performance of the chosen operating platform. And if we consider the numbers of healthcare processes in Italy, assuming a uniform distribution of processes throughout the day and therefore not evaluating peaks at certain times, we have that the theoretical performance of the blockchain can amply support the load of transaction required by the healthcare processes. From the graph, it can be seen that the number of possible transactions in Hyperledger fluctuates around 1,000 per second, while the number needed to cover the processes is only a few transactions per second. So, in conclusion, we can tell that the validation of healthcare processes is a crucial point, and the architecture we are proposing aims to solve this problem. The case study shows how the use of such a system is feasible, both in terms of process adherence and performance, and the development of a prototype is currently underway, after which benchmark tests will be carried out. The work was carried out with my colleagues in the CNR Interoperability and System Management Group, and here you can find my contact information, and in the site you can find information about all the members of all of the team. Thank you for your attention.
Thank you, Fabrizio. I have a question and an observation. Let's start with the question. You used in your architecture, you used the Hyperledger Fabric. What about the possibility to switch to traditional ledger technology such as Ethereum or Algorand?
Okay, the architecture as such is transparent to the blockchain platform of use, but it's certain that the choice affects the system, and the use of Hyperledger Fabric is a consequence of various evaluations. The platform must allow the use of permissioned technology and enable the programming of smart contracts. Ethereum, for example, has these characteristics, but is strictly linked to tokenization, and in an healthcare context such as the European one, based on public healthcare, use a platform linked to cryptocurrencies will be a wrong choice. Moreover, there will be management costs and organizational constraints, for example, linked to the platform itself. Hyperledger offers the possibility of designing the blockchain in-house by providing cloud services that are not mandatory. In addition, there is a modular approach that allows a high level of customization. So basically, we can use also different platforms, but at the moment, Hyperledger seems to be the better choice.
Okay, thank you. Just an observation. I saw that you, for validation purposes, you use the number of the Italian patient and prescription.
Yes.
Since we are starting from the point where interoperability in Europe is very important for the prescription and the prescription feature, I would suggest to go to let's say to the countries with the higher population and higher rates of immigrants that could be together asking for prescription. That's just an observation for your future work. Thank you.
Yes.
And
Okay.
let's go to the next presenter, who is Gustavo Gonzalez-Granadillo. Hello, Gustavo. Gustavo will present as a multi-factor assessment mechanism to define priorities on vulnerabilities and affecting healthcare organizations. Thank you, Gustavo.
Hi, thank you. Can you see my slide?
Not yet. I can see you. Okay, now the slides are loading.
Okay, perfect. So
just
good morning,
a moment.
everyone.
Okay, now it's okay. So, thank you.
It's fine. Okay. So good morning, everyone. My name is Gustavo Gonzalez. I am a cybersecurity research engineer at Atos, Spain. And today I would like to present you one of the research I've been doing in collaboration with the University of Piraeus that we called a multi-factor assessment mechanism to define priorities and vulnerabilities affecting healthcare organizations. So this is actually part of a project that we call Curex. This is involving several healthcare organizations, and we are proposing several tools. And this is actually one of the functionalities of Vulnerability Discovery Manager tool we call VDM, which is a software component that can work as a standalone tool or as a combined solution, and that has been designed and developed within the context of this project, the Curex project. So in terms of motivation of this research, the work lies basically on the increasing the number of threats and attacks against the healthcare domain. The fact that there are no standards and good practices specific to vulnerabilities in this domain, the information sharing issues that prevents vulnerabilities to become known to the public and to the industry, and the fact that vulnerabilities assessments relies mostly and solely on CVE and CVSS metrics. And last but not least, the fact that current security measures seem to be ineffective. So all of these makes us believe that there is a need for domain-specific cybersecurity tools and solutions. So in order to cope with the need, we have developed this Vulnerability Discovery Manager, whose main role includes the discovery, identification, and classification of vulnerabilities to the system assets, the assessment of the discovered vulnerabilities, which allows us to assign priorities based on their scores, the treatment of these vulnerabilities that exceed acceptable levels, and intelligence sharing functionalities with other hospitals and communities. Our tool has four main components. The vulnerability scanner that will basically receive as input the IP addresses associated to the different assets that we have in the target system. Here what we do is we are going to check against external databases and CVS what are the vulnerabilities that we can identify for these particular assets. Then we are going to store in the vulnerability storage. We keep all the information associated to the vulnerabilities. And then we go for a vulnerability assessment process that includes several steps. And then in the end, we are going to provide vulnerability analysis to the reporting and intelligence sharing. So this part is one of the crucial part, because we have the possibility to share the report with other communities and inform other organizations about the vulnerabilities in the assessment that we have already taken. So since assessment is one of the main part in our research, we are going to be focusing today's presentation only in this block, the vulnerability assessment and the methodology that we are following in order to improve the current assessment that we have right now. So as I said, traditional assessments rely on CVE and CVSS metrics. However, the impact of a given vulnerability can vary from an industry to another. Therefore, the need of a specific domain-specific security tools is a must. For the computation of the vulnerability assessment, we propose to focus on three main groups of data. We have the root cause, impact, and remediation. So the root cause identifies and assesses the main aspects that could lead to the exploitation of a security vulnerability. Then the impact of a given vulnerability, if exploited in the system or network, is going to be carried out in this second parameter. And the remediation actions that are needed to recover from the successful exploitation of a vulnerability is considered in the third parameter. And so the mean of these three parameters will be a score from 0 to 5 that will tell us how what is the assessment on the vulnerability levels that we have identified. Going more into details in terms of the root cause, we have proposed several let's say features. So we have, for instance, identified potential factors like the human factor, design flaws, failures, complexity, etc. So that could directly or indirectly be the origin of the existence of a given vulnerability. So each factor has been assigned a score based on expert knowledge, and we have considered the possibility of adding other factors. So this is actually quite flexible and can be enriched by the expert community, or indicating, for instance, that the factor is unknown, so we don't know exactly the root cause by the time of the analysis, and therefore this parameter is not going to be considered in the score computation. Then the second parameter, impact, is formed in association of the three other parameters that we call the data at risk, severity, and damage. So the data at risk assesses the type of information that needs to be protected. For instance, we have personal identifiable information, financial data, intellectual property data, social media accounts, etc. So all of these will have a score based on the let's say the protection that requires this kind of data. Then the second parameter is what we call the severity, and is directly considering the CVSS, the Common Vulnerability Scoring System. And so we basically do not do anything, we just rely this into a score from 1 to 5. And then the third parameter is about the damage. So the potential damage that could be caused by if the vulnerability is successfully exploited is considered in this, and it can be a total damage, partial, no damage at all, or even if we don't know exactly, then we can also indicate that there is no information available for to assess this parameter, and then it's not going to be considered in the computation. Again, this let's say the mean of these three features is going to give us a score for the second parameter used in the equation, which is the impact. So we are going to have an impact from 1 to 5, and then we are going to go for the third parameter, the damage. The third parameter on the equation is the remediation, and this is basically assessing the potential capabilities for an organization to implement and recover for a successful exploitation of a vulnerability. It considers several other parameters, like, for instance, the recovery time, that could be short, medium, or long, the types of measures required to be completely recovered. So if we need new measures or existing ones, or if we don't need to do anything to recover, the actions needed by the target system to keep on running. So this is actually what we call the resilience, how resilient is the organization, the systems. The level of cost associated to the implementation of security measure that can be low, medium, or high, and the recovery level. So after the exploitation of a given vulnerability and implementing some countermeasures, are we going to be partial, total, or we are not going to be recovered from this? So all of these, let's say, conditions are considered in the remediation level, and we have also a score for each of the let's say, subparameters in order to compute the remediation score, which is actually also scored from 0 to 5. Then, just to give you an example of how we can use this, we evaluated a vulnerability of a remote code execution detected in a server from a healthcare organization. So the first step was to compute the root cause. And so since this can be associated to multiple causes, like for instance, open connections, weak passwords, complexity, human factors even, or a combination of some of them, so this parameter is set up to 5. Then the second step is to compute the impact. And here, since the vulnerability could lead to the exposure of medical information, the data at risk is set to 5. We know that the CVSS for this vulnerability in particular is 10. So the severity is also set to 5. And since the system is expected to be partially damaged, the damage score is set to 3. And as a result, the impact value for this CVE is 4.33. The final step is to compute the remediation. So in this case, we know that the system can be easily recovered in a short period of time. Therefore, the recovery time is set at 1. It requires implementing new security measures. So the requirements is set to 5. It doesn't require to remove the vulnerability to keep running. So in this case, the resilience is set to 1. We don't have information on the cost of these, let's say, countermeasures. And so we are going to set this value to 0, and actually this parameter is not going to be used in the computation. And then we know that we are expecting to be fully operative after the implementation of the mitigation measures. And so the recovery level is set to 1. As overall, the remediation value is equivalent to 2. And in this case, what we do is to compute the mean of these 3 parameters, so 5, 4.33, and 2. And the final score is 3.78, which we consider it's a high level, and then it should be stated with a high priority. This information is mostly based on theoretical parameters. So we are also expecting to be validated by the operator in a real environment before being shared with the other organizations and communities. So the final goal of this, let's say, the research is to have a public repository with information of the validated scores to compute the average risk of a vulnerability per domain and keep all the communities of interest informed and updated. And so to wrap up the presentation, we have developed a vulnerability discovery manager aiming to scan, store, assess, and share vulnerability reports to organizations and communities. The mechanism proposed to perform the vulnerability assessment considers multiple factors such as root causes, impact, and potential remediation actions. The output of this process is a score that ranges from 0 to 5, and that can be used to assign priorities to the analyzed vulnerabilities. And then future work will concentrate on evaluating other features and computing scores in a large-scale network for health organizations. So thank you for your presentation, and I will be happy to answer any questions if you have.
Okay, thank you, Gustavo. Just one question. You say that you know that in current cybersecurity landscape, it's very important threat intelligence activities. It is very important the possibility to share and disseminate information taken from analysis at any organization, at any individual organization. Does your tool support any kind of information sharing feature?
Well, actually, yes, we have, we send this information to the MISP platform, and then let me show you. We have here the website in which we have this information shared with other communities, and then what we can see here, for instance, the example that I have already showed, the remote code execution, we have publicly available this information, and we can also go further and check for more details and have this, let's say, the information, consumed by other organizations, by other communities, and the final idea would be to just keep track on the information that is shared by the same type of community. Let's say that the industry on the healthcare, we just let's say invite different organizations to use our tool to give us a feedback and also to validate the scores. For instance, I mean, these scores are mostly theoretical and they are based on expert knowledge, but we need actually the validation of the end user. In Curex, we are validating with 3 healthcare organizations, but we plan to do it further with a much larger number of organizations in which we can finally decide, okay, this is for instance, for a particular CVE, regardless of specific organization, we just can say that for the domain in general, the healthcare, we have a score set up to, let's say, 3, which is medium, for instance. And so in this case, what we can alert, all healthcare organizations that are in the community to be aware of these new vulnerabilities that is coming, and with the evaluation that we have also provided. So yes, we are using, as of now, the MISP platform to share this threat, to share this information, and to also select, the type of sharing that we want to do. Do we want to share it with just a small organization, with a big community, or with everyone? So we can also have these options in the MISP platform.
Okay. Thank you, Gustavo. And let's go to the next presenter, who is Giovanni Mazzeo. He will be telling us about facing the blockchain endpoint vulnerability, an SGX-based solution for secure health auditing. Giovanni, please go ahead.
Yes, just to verify, give me a second because I'm not able to. I have to leave. 1 second, I have to leave the event.
Okay, in the meanwhile, Giovanni reconnect. Gustavo, please forgive me, I didn't see your question for the previous presenter because it was not in the question and answer section, but in the chat. So this,
no problem.
I didn't see. So Giovanni, are you back?
Yeah, I'm back. I'm here. Give me a second. Let me also start the video. Okay. So can you see the screen?
Your browser. You are sharing your browser.
Yeah. No problem.
Okay. Perfect.
Here we are. So yeah, thank you. I'm going to present the work that a joint work that was done between the University of Naples Partenope and the Bit4ID company in the context of a European project, namely Confido. We all of us know the problem that we are facing here. This is also why we are here for. That is facing the huge amount of rising attacks that are coming against the e-health sector, and therefore protect both the privacy and in some cases also the integrity of the confidentiality, and in some cases also the integrity of data, of patients' data. In the market of security solutions with a particular focus to the e-health sector, we are witnessing the adoption of blockchain technology for the security enhancement of different aspects, different features of e-health based systems. The blockchain is used for the protection of both patient data, record management systems, and also for auditing, for the protection of auditing systems. However, the blockchain is not the panacea. It is affected by a weakness during the ingress and the ingress phase to the blockchain, where the system has to submit, has to insert the data, or also when it withdraws the data from the blockchain. In that specific point, we discussed in our paper the so-called endpoint vulnerability. This is a weakness that affects most of the blockchain-based systems, and it was also discussed in literature from researchers, and there are some possible approaches that can be adopted to face such a vulnerability. So we know this. We want to give me a second. Sorry. We want to highlight that the vulnerability of the systems can occur actually when the data has to be provided into the blockchain. What happens is that most of these solutions run in untrusted systems, and the possibility that malicious users access the hosting machine is something that is concrete. And in that case, when the malicious users can obtain control of the hosting machine, they can manipulate the data before the insertion into the blockchain. We studied a possible solution for this weakness during our work on a specific case study that we had in our project, in our European project, which was a blockchain-based auditing system for the protection of logs belonging to the European e-health management system. Basically, in the Confido project, we implemented a number of solutions, of security solutions, to enhance the security of the so-called OpenMCP, of the OpenMCP tool. OpenNCP, sorry, European Health Management System. And above all, we provided a blockchain-based auditing system that aims at ensuring the integrity of logs that are generated during the execution of the e-health management system. What we did was to use a proprietary solution, namely Hylos, that was provided by the Bit4Ready company. This proprietary solution basically is shown here. It pulls logs from the OpenNCP software and encrypt this log. They generate the hash of the log and provides them into the blockchain. And the same process is applied for all the other countries. So we have in the OpenNCP infrastructure, we have several national nodes that interact between each other, and all these national nodes are used to exchange e-health data between countries. Each of these nodes have generate logs, which are quite critical for the security of the overall system. And in our solution, we equipped the national contact point, the national nodes, with this blockchain-based auditing system. What can happen is that attackers could tamper the logs when actually are generated into the NCP, that is the national contact point, the node that represent each country, and is used to to exchange data with other countries. Now, the point is why log security is important for us. It is important for us because if attackers manipulate logs of the node, they could not only manipulate data of patients, but also of activities made on patients' document. But also they could, for example, hide their location, or they could hide malicious actions that were made on the machine. So this is why the security of log is fundamental, because without solid logs, we could assist, we could observe, we could not observe or identify malicious actions made on the system. What we have done was to extend the solution that we thought, the blockchain-based auditing system that we provided in the Confido project, using an hardening technology which is known as Intel SGX. Intel SGX is an extension to Intel's CPU instruction set architecture that allows to allocate private regions of memory, namely secure enclaves, which are protected even from from software that runs on a privileged level. So, for example, at ring 0 level. The concept is like the concept of a reverse sandbox. So the sandbox tries to protect itself from the outside system that is considered untrusted. With SGX, it is important that with SGX, the advantage of SGX that the process memory never leaves the CPU package unencrypted. So the dedicated memory that is allocated for the secure enclaves is always exit the CPU encrypted. How we used SGX? We basically equipped the so-called national contact point nodes. So the national nodes that I remind you that these are the nodes that exchange the e-health data between countries. So we extended these national contact points with SGX enclaves. We basically receives, maintain information on patients encrypted outside of the SGX enclave, perform sensitive operations on patient summaries within the SGX enclaves, and generate logs into the SGX enclave. Here we encrypt and sign the logs, and also, most importantly, hold all the needed keys that are, for example, private keys or other symmetric keys that are needed, for example, for the encryption of patient summary, and preserving this way the security against the malicious users that take control of the node. Once we generate the logs into the SGX enclave, and then encrypt and sign the logs, and then we send this log to the blockchain by establishing a TLS terminated communication that ends actually in the SGX enclave. So in this way, we are not exiting the enclave for doing the socket for the transport to the blockchain. Another important thing that we had to face was the key management, and in particular for the protection of data coming from users, for protecting the data coming from the data related to users, to patients. We had to define a setup phase where we attest the security of all the enclaves. In this way, we are sure that all the communicating parties are measured and integrity verified. So we have we have N countries that contain an SGX enclave, and each of them establish a mutual attestation procedure. And so in this way, we will have all the national contact points that will be integrity verified. They will exchange data with the Diffie-Hellman key exchange protocol that allows the enclave to exchange keys without exposing any sensitive information in the channel. And at the end of this setup phase, that it is quite slow, but it's not of interest for us because it's a setup phase that is run once or periodically with a low period time. So at the end of this setup phase, the different nodes can do the business for what the application was implemented. Finally, we performed an experimental evaluation using a local testbed. Basically, in this case, we didn't care about latencies or all the other let's call them noise sources that could come from a real setup. But we were interested to understand the impact of our solution in terms of log generation and log sending. We implemented a local NCP Docker-based testbed, connected them to the blockchain network, and configured the 20 peers to perform the evaluation. At the end, the overhead that was observed was of 8% for what about the log generation, while it was of 23% for what about the log sending, I mean, in the sense of log transmission. Here, this was a bit higher, because while the log generation involves no much context switches between the secure and non-secure world, the log sending instead requires the adoption of an SGX extended TLS library that introduces an additional source of overhead, and therefore we observed a higher overhead. And well, I'm done, and I'm open to questions if there are any.
Okay, thank you, Giovanni. Just one question. You presented the overhead you recognize in your system. How it is compatible with the actual data volumes that are expected for the system? Did you evaluate this?
Yeah, basically, we during in the context of the project with our partners, so we discussed this problem and defined the worst condition scenario. So in this worst condition scenario, we studied the statistics of the different countries and took the one with the highest number of EU immigrants and citizens that would query the national contact points. So with the worst condition scenario, where all of them have to get access to their patient summary, we defined a rate of 600 patient summaries per hour. So it's a low number. And given that each operation of patient summary transformation and provision requires something like 4 kilobytes of logs, this is something that is completely reasonable.
Okay, thank you. If there are no more questions, I think that this session can be closed. It was interesting to discuss with you of these topics related to health security. I hope the audience enjoyed the discussion. Thank you all.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.